The same religion that's capable of hideous acts of destruction can also be capable of moments of healing, of restoration, and of hope.
But educate a girl, and you educate her entire family.
There is a sun within every person.
When that anger sets in, write it. Write the letters, but don't send them. You never want to leave concrete proof of insanity.
Well, first off, I'd like to thank you for the introduction, and also to Susanna and the rest of the organizers for the invitation to come. This has been a great week of science for me to participate in, and I'm going to shift gears a little bit, and as he described, this is going to be more a talk about the market conditions that are impacting the chemical industry and how technology then plays into the potential solutions. So what I'm going to do is try to lay that out for you, what the different challenges are, the approaches that companies are betting on, and then therefore the enabling technologies that are going to be needed to deliver on those. So as was said, the title is Redefining Feedstocks for the Chemical Industry, Opportunities and Challenges for Catalysis. What I'm going to do first is lay out for you an overview of the challenges, and then focus on three areas where there are developing technologies, but specifically challenges to utilizing three new feedstocks, and those would be methane, coal, and biomass. And I'll have some good examples, I think, of technologies that are enabling those, but also the challenges that are preventing commercialization of those technologies. And then I'm going to touch at the end on some examples of ongoing research at Dow to give you a feel for the kind of approaches that we're taking to try to address some of these issues. So when you look at the chemical industry and you look back to its inception, it's really gone through a number of technology waves. If you look from the 1760s up to the early 1900s, the chemical industry was really built on inorganic materials. It was, as we define feedstocks there, I think it's listed as rocks. Dow Chemical was founded on electrolysis of salt. So electrolysis of salt to produce chlorine and bromine, which was then used to produce inorganic materials, and then later functionalize organic materials with that chlorine and bromine. Really that shifted in the mid-1800s, again to later in the 1900s, to coal as a feedstock, and really to functionalization. To using inorganics to transform organic materials and to make dyes, solvents, and drugs. In the late 1800s to the mid-1930s, what also began to emerge is biomass as a feedstock, and really this was really the first polymeric materials that we became familiar with were a result of biomass. We used inorganics to transform natural materials, and we made partially synthetic polymers. And two examples, obviously, would be rayon and cellophane, both based to some degree on natural materials. Really, it was just before World War II into the present time that what really dominated the chemical industry, and I'll show you some specific examples of that, was the polymer industry. And this took off really with synthetic rubber efforts during the war, and then afterwards with really the growth of polyethylene and now more so polypropylene, and basing our feedstocks now less on coal, but more on low-cost petroleum and natural gas. And that's really what took us to, I'd say, the more recent present. But really the question for, I think, this group, and I think what will come out in the Q&A, but also in this talk, is, what's the next technology wave? And there are a number of things facing the industry, and those are the ones I have listed at the top. Raw material competition, you're going to hear a lot more about that. New materials, energy, and the energy issues facing the world today, and CO2. These are things that we're all familiar with in terms of challenges for the world, both from an environmental and an economic standpoint. And the question you have to ask is, what are the potential feedstocks that are going to impact those areas? And again, I'm going to focus on methane, coal, and biomass. There certainly are others, but those are the primary ones that I'm going to focus on today. But again, we can't predict necessarily what those new technology trends are going to be, but we can at least kind of highlight where the industry is going and the challenges that we see today. But before I do that, I want to sort of ground everybody, because there have been a lot of comments made this week and in the literature on understanding issues like CO2 and the hydrogen economy and other things that have come up. And what I want everybody to come away with, if there's anything from this talk, is that we as the chemical industry use energy. Our feedstocks, our coal, our methane, our oil, those are fuels as well. And so when you think about carbon balance in a chemical process, it's not just the carbon balance of what you put into what you make, you also have to include the energy used to do that, because it's all carbon. And so we have to start rethinking, looking at the overall thermodynamics of a process and how both the feedstock carbon balance and the energy utilization impact the overall economics. So what I've shown here is just what does the global energy look like. And what you see is that chemicals, and these bars are proportional, the chemicals make up a very small percent of the global energy usage, and it's about 6% of total industry, the total energy use, with industry being the predominant use of energy, but chemicals being a very small part of that. When you then look at chemicals themselves and you say, how is the energy in chemicals being utilized, about 70% of it is in organic chemistry and polymers, with a smaller amount into inorganic materials and agricultural uses. But again, the important thing to note, and if you look at the bar to the right, the chemical use of energy in organic chemicals and plastics is only half in the actual feedstocks itself. The other half is in the energy used to convert those feedstocks. So at the end of the day, the actual amount of raw material in terms of energy that goes into making chemicals itself is very small. It's again 3% of the total energy use. The bulk of it is actually in energy itself, in terms of fueling the turbines, doing the separations at all. And what is the foundation of that chemical industry? Well, it's a steam cracker, and I'll explain that a little bit more in terms of technology, but the chemical industry's foundation is on steam cracking of natural gas and oil. And ethylene is the result of that, and ethylene is the largest volume organic chemical intermediate produced in the world today, and ethylene and propylene derived chemicals dominate the industry. So it's very important for us to understand the feedstocks that we use to make those materials and how impact of globalization and market factors are impacting what those feedstocks are going to have to be in the future. So what does the industry look like? Again, this is just a schematic to give you a feeling for the flux of materials, and again, these are proportional arrows to kind of give you a feel of Dow specifically, but this is probably representative of the industry as a whole, where the raw materials go. So we get our raw materials from ethane, which comes from natural gas, and from naphtha, which is a cut from oil. We are about 57% naphtha dependent, about 43% ethane dependent. That goes through a steam cracker, which basically takes steam and those raw materials and at high temperature cracks those, in the ethane case to almost pure ethylene, and in the naphtha case to mixtures of ethylene, propylene, and higher materials. And those materials are the foundation of what Dow makes today. So 60% of our products are based on ethylene. So 60% of everything that Dow makes, and for the most part, large chemical companies in general, is based solely on ethane or naphtha as a feedstock. The big products, obviously polyethylene is the largest. Ethylene oxide, vinyl chloride, styrene, vinyl acetate, these are sort of the primary materials that Dow makes. And from propylene, we heard a lot of talk. This will be actually, I probably lied to you, there will be one comment of propylene to propylene oxide. I do show it here, I think. But propylene oxide is the largest material made from propylene within Dow. And as shown in the presentation earlier today, that's via chlorination technology that we're obviously trying to develop alternatives to. Polypropylene, butanol, acrylic acid, and then to a small degree a number of other materials. But this gives you a flavor of really what the industry does. But again, almost 90%, if you add up the ethylene and propylene, 90% of what we make has a foundation in those raw materials. So what are the challenges to the industry? And actually you in your introduction touched on this perfectly. It used to be, and this is a historic tracking of the costs of crude oil, natural gas, and coal from the 1950s up till, I think this is 2004, so actually the peaks will probably be a little bit higher if we were to look at them today. But it used to be that low-cost natural gas in the Gulf Coast enabled chemical companies in the U.S. to produce all their products in the Gulf, for the most part, and ship them anywhere in the world and be cost competitive. And that would be a reason why, if you travel to Houston today, you'll see a large number of large petrochemical complexes located in the Gulf Coast. Again, the advantage being that natural gas was substantially lower in cost than oil, and so regions where they were dependent solely on oil couldn't compete with the cost, and therefore globalization from a marketing standpoint could happen without having to globalize your assets. Now, what you've seen, though, and what's listed here as BTU parity, is that if you start looking in the mid to late 90s, what we see is that natural gas and oil are now essentially equivalent in price in the U.S. And the challenge there then is you can meet your market needs in the U.S., but you can't produce chemicals in the U.S. and be competitive worldwide. Now, we don't use all the sophisticated journals that a lot of the researchers here do. You know, we pay a lot of marketing companies to predict the trends for us, and you know, here you see no more oil. You know, world supply will be gone in 6 months. We obviously hear these. We see it in the news every day, people projecting this is going to be the case. But depending on how much you pay your consultant, you can get a different answer. So oil found on the moon, you know, gas prices will fall to 10 cents. Well, obviously these are meant to be a joke, but the reality is we don't really know what oil prices are going to be. The reality is a company, you can't bet on one feedstock to be competitive in the future, that we have to have a balance of options. And this is really what this slide is really meant to represent, that as we grow, and we grow in the U.S., and we grow in the Middle East, and we grow in Asia, we really have two options. We can decide that our feedstock portfolio is going to be what it is today, and that we just need to get more and more of that, and that would be oil and natural gas. But the reality is, for us to be competitive, we cannot ignore other potential feedstocks to mitigate the risk of the volatility of these feedstocks. And you know, coal, methane, biomass are three primary options, and those are the ones that I'm going to touch on today. But really where Catalysis plays in then is utilizing these materials, we're going to have completely new innovative technologies and processes to take advantage of those feedstocks. We're not going to be able to make the materials that we make today. We're not going to have the same intermediates, and we're not going to be able to use the same assets that we use today. And that gives us, you know, a lot of promise in terms of new technology, but also a lot of risk. And so this sort of, to me, summarizes the trends that are facing the chemical industry. We've got to expand the feedstock portfolio beyond oil and natural gas, or in oil and I'll say ethane specifically in natural gas. And again, I've listed those three options. But those new feedstocks are going to do a couple of things that are going to cause problems. You're going to make new materials as intermediates that you don't make today. And so you're going to need new technologies to utilize those, and you're going to have a new slate of potentially new products as well. You're going to have to develop new improved processes that improve your energy efficiency, improve the carbon management, and improve capital costs to make these technologies viable. And at the end of the day, energy is really the issue here. Our feedstocks are fuels to everyone else. We're competing with the fuels market for the same carbon. And so it's not just your efficiency of taking that carbon and converting it to the olefin or the aromatic that you want, but it's also the overall energy consumption that goes into that process that you have to keep in mind. There have been a lot of comments on CO2 management, and I'll touch on that a little bit later, but you know, the challenge is we're going to produce CO2 in a lot of processes today, and actually if we go to coal and other materials, we're going to produce more CO2 than we have in the past. There are ways to convert CO2, and people have made, you know, questions about activating CO2 or hydrogenating it or converting it to other materials, but all those, you have to keep in mind, require energy to do that. So even though your carbon balance is very good, maybe you can take CO2, you can hydrogenate that to methanol, and that from a carbon balance is very good. The problem is you produce more CO2 to produce the hydrogen you need to convert the CO2. So at the end of the day, we have to think about the overall picture, and at some point there's going to be a balance of the cost versus the environmental impact. So what does the natural gas picture look like? Well, what I want to show here is we take ethane out of natural gas. It's less than 5% typically of a natural gas field, and that's what the chemical industry uses to make ethylene. The bulk of the natural gas here is either used as fuel, and that would be the optimum use, or it's flared. And in many cases flared because it's in the way of the oil reserves, and so typically has lower value to those that are trying to access the oil. We then again take that through a cracker, we make ethylene, propylene, but we're not using a bulk of that natural gas. So what does the natural gas picture look like globally? Well, the real challenge, and again, these numbers are from last year, so that they've actually improved slightly, so I don't want to make the picture look quite as grim as it was last year. But the U.S. paid more in natural gas prices than anywhere else in the world. Now, again, that has huge commercial implications for a company like Dow. I mean, it really does say that you have to look at other options to take advantage of low-cost feedstocks, other locations. Now, the problem, again, is that we're competing for these low-cost reserves with the fuels industry, who also cares about converting cheap natural gas. So you're competing for the reserves against gas-to-liquid processes, LNG processes, ammonia and methanol synthesis. And a bigger issue, which is highlighted in the pyramid at the bottom left, what you see there is units of TCF, so that's trillion cubic feet of gas. And just to calibrate everyone, if you want to go build an olefin complex, so you're going to build a world-scale commercial plant to produce ethylene, you need something in the order of 1.5 TCF of gas to be able to afford to do that. And essentially, the reasoning is you're going to invest multiple $billion in a fully integrated facility to convert gas to olefins. So you need to depreciate that capital over enough time to make that economically viable, and that would be roughly, I'll use a number, 20 years. Well, if you look at the pyramid and you say, okay, how many gas fields have 1.5 TCF of capacity? Well, there's a huge amount of gas in the world, but you see that the 1.5 TCF, if I use my cursor here, that would be this region right here. So what does that mean? Well, there's a huge R&D challenge and opportunity, which is if we can take advantage of smaller gas fields, which are typically very low in cost, and develop technologies that allow us to convert that gas to a shippable intermediate so that we can invest much smaller capital at those locations, but ship that intermediate to other locations to produce product, we have a huge opportunity. An example would be, could you take methane at a stranded site where the gas is, I'll pick an example here in the Middle East, where it's less than $1 a million BTU, so it's 1/10 the cost in the U.S., and convert that to methanol and ship the methanol to somewhere in the world and convert that methanol to olefins. And what that requires then is being able to develop technologies for alkane activation. And selective oxidation, as discussed during this week, is a huge potential area of research and an ongoing active area of research. And also other options, and I think this will surprise a lot of people that haven't really heard about this, is that there are a lot of options that include an FPSO, which is basically a floating platform. So it is viable to build a barge that would take access to this low-cost natural gas, convert it to a shippable intermediate, and then when that field runs dry, you just move that to another location. So these are the kind of options that are out there, but really the key point is that there's just not a lot, there's a lot of gas, but it's not in locations where you can build a traditional facility. So when we look at methane conversion, I'm just going to touch really on more syngas than the others, but there are really three primary ways that we can try to convert natural gas. They're the syngas methods. And I'll go into more detail, but the issues with syngas is the cost of generation of syngas is very high. From a capital and an energy standpoint, it's very high. But it is commercially practiced today. So if we look at sort of the cost-benefit analysis, we can do syngas. We could make our products via syngas, but it's going to cost us a lot to do that. And there's going to be risk associated to some degree, but it's really more of a cost issue. There are some direct methods, and you'll probably hear more about that from the research at Dalian, I think either the end of this week or next week, on methane coupling or methane to aromatics via direct conversion of the methane. There are issues there. There's selectivity problems, which lead to separations problems. There really is a need for a significant performance leap in the technology to make it viable. And there are other issues, like operating within the flammability limits. I mean, if you want to convert methane to methanol via oxygen, there are limits as to how much of a conversion you can have in that process and still maintain safe operation. And then there's the last area, which has had actually some considerable advances here with GRT in the Santa Barbara area on heteroatom functionalization. So can you convert your methane to something that's functionalized with a heteroatom, such as a halogen, for example, or a sulfur-based material that allows you to ship that material or to get higher selectivity in the conversion, and then you could subsequently convert that to olefins. The problem there is a new problem, which is you've got to have complete recycle of whatever that heteroatom is. You can't afford to lose bromine or chlorine or sulfuric acid, base materials in that process. So you have to have complete recycle, and you've now added another step in your process. But these are the kind of options that are on the table, and like I said, each has real opportunities, but each has real challenges. But when I talk about syngas, what do I mean? Well, the beauty of syngas is that syngas works with all the feedstocks that we talked about. So we could take natural gas, we can take oil, we can take coal, we can take biomass, we can take waste recycle. We can react that with oxygen or with steam, either in partial oxidation or in steam reforming, depending on which route you choose, to make CO and hydrogen. And the beauty of that is, again, from a range of raw material supplies, you can make a unified intermediate of CO and hydrogen, which can be used to produce methanol, ammonia, or fuels through Fischer-Tropsch to Fischer-Tropsch liquids. And the beauty of all this is that all this is commercially practiced today. So from a technology standpoint, to make those intermediates, there really is no risk from a technology standpoint. The only step that would really have to be implemented to produce olefins from that would be something to convert the methanol to olefins, and there is technology, and many of you I'm sure are familiar with Mto Technology, and certainly our Dalian representatives are familiar with it. This is not commercially practiced today. It has been demonstrated, but again, it has not been commercially practiced today only because of the issue of what's the methanol price and is it going to be economically viable. It really requires somebody to say, this is going to be the way it needs to be done in the future. So what does a process look like for MTO? And again, I've taken one example of an MTO process. There are a number of others, but this is using standard technology where you would feed oxygen and natural gas to an autothermal reformer. You would do some partial oxidation to generate the heat needed to drive the endothermic chemistry. You would make syngas. You would convert that to, to methanol. And then you would take that methanol through an MTO reactor using a zeolite, which is what MTO is based on, to convert that methanol to ethylene and propylene. Everything in the red box is commercially practiced today. This is how methanol is produced that you purchase today. It's typically made in recent days, very large-scale production at about 5,000 metric tons per day. So it's all viable. The methanol to olefins piece, again, has not been commercially practiced only because of just competing economics versus an ethane or naphtha cracker. And I think there are a lot of announcements, and if you read the open literature now, you'll see a lot of announcements for movements in this direction now because of the potential competitive nature and the high cost of oil and gas. But again, a challenge here is a world-scale cracker equivalent, a world-scale complex to make ethylene is going to be 2 times the world's largest methanol production today. So again, you're having to take a huge step in both scale and in new technology, which again has risk. But from a stoichiometric standpoint, natural gas to olefins looks very good. You start with 1.2 metric tons of methane and produce 1 metric ton of olefin, and the byproduct is water. So you're really from an overall stoichiometric standpoint, it looks very good. But this gets to the point I wanted to start my talk out with, which is it's not just the carbon stoichiometry of inputs to outputs that you care about, it's also the energy that goes into that. And what's shown here is a comparison of the energy demand for an ethane-based cracker, which is really the foundation of the industry, and a syngas-based conversion to olefins. So here's the overall energy demand for converting ethane to ethylene. Here's the overall energy demand for converting natural gas to ethylene via syngas. And what's broken down in the arrows here is just to give you a relative frame of reference on how much energy each step in the process requires. So 60% of the energy demand, roughly, is in synthesis of the syngas, which is the ATR here, and conversion of that syngas to methanol, with a very small cost of the energy to convert that methanol to olefins. But what you see is about twice the energy demand to do a syngas-based route. Even though the carbon stoichiometry of the inputs and outputs is very good, the overall carbon balance is actually pretty poor. And you see that here in terms of just, again, but the higher energy leads to one thing, it leads to more CO2. That extra energy is just combustion to drive the process, and so you're producing CO2 from it. So that's one of the reasons, again, the high capital cost of syngas and the energy demand versus known technology based on ethane that we have access to, that no olefin production currently is being made from methane. Now, methane does serve as a basis for chemicals, although to be realistic, those that follow the industry will find that methane as a source of chemicals is dwindling quite rapidly because of low-cost coal that exists in other locations. And so, in fact, ammonia synthesis via coal is really dominating the industry and having a huge impact on U.S.-based methane conversion to ammonia for fertilizers. So when you talk about other feedstocks, this captures for you the overall potential reserves of feedstocks. It's hard to ignore coal as an option. Clearly, gas and oil are roughly similar amounts in comparison, but coal, in terms of potential future feedstocks, dominates the options that are out there. And the U.S. is really, and China together, make up the bulk of coal as a feedstock. In fact, the U.S. has quite a large coal reserve, so it would be a very viable U.S.-based feedstock to utilize as well as for growth in China. So again, a coal to olefins process is viable as well. And again, everything in the red box is commercially practiced. And instead of calling it steam reforming, we would call it coal gasification now, but basically taking coal to send gas into a methanol reactor. And again, at that point, you would have methanol. You would do the same step. You would do an MTO step. Again, this is shown for MTO. The single world-scale olefin complex greatly exceeds the current coal-based methanol process. So again, you're going to have to invest more capital at a larger scale than has been done before. But the issue with coal compared to natural gas is a new one. In the coal case, you're deficient in hydrogen versus methane. So when you start with coal, you take that coal, you react it with oxygen, you produce 72 equivalents of CO and 30 equivalents of hydrogen just based on stoichiometry. The problem is that's not enough of a ratio to generate methanol. So you have to get that hydrogen from somewhere, and you get the hydrogen by doing water-gas shift. So you add water, you shift your CO to CO2, and now you end up with the little over 2-to-1 ratio of hydrogen to CO that you'd like to have, but you produce 40 equivalents of CO2. And if there's any issue with coal, this is the issue. And from a technology standpoint, conversion of coal to olefins is a valuable route. But we all have to come to grips with the fact that we're going to have a huge impact on CO2 production with any coal facility. Now, there are technologies for sequestering and addressing it, but I think we just all need to be aware of the differences here. Now, if we look at energy demand...
This cause shortages of water?
Well, water is a huge issue, like in developing areas, like if you're going to build a facility in China. I mean, making sure you have access to water is a critical issue that gets assessed in these facilities.
I guess using 40 moles and you get out 32.
Yeah. So here's the energy demand comparison again. And what you'll see is that for the comparison with natural gas, the energy demand is the same. What you have different, though, is the CO2 production. And again, that comes from that having to do the water-gas shift process to get the CO to hydrogen ratio that you care about. But again, from an energy demand relative to natural gas, this is very competitive. It really comes down to a couple of issues. One, you have to use more coal in terms of mass to get the ethylene you want because of your shift. So the plant needs to be bigger, so there's more of a capital investment, but the energy is roughly the same. So, and the technology is all very viable. So these are really good options to consider. And in fact, there are many development plans in place and many pilot units developing this technology. But there are issues, and the issues really come down to higher cost and addressing the energy demand that these processes rely on. And what that really means is if you have access to ethane or naphtha at a comparable cost, you're not going to take the risk. But if you're growing in a geography where you need access to low-cost feedstock, you have to address the option. And that's one reason why in China, clearly coal to chemicals and coal to olefins are very serious opportunities that have to be evaluated. But we can't do so and ignore the fact that we have to do something to address the CO2. So biomass-based feedstocks, we don't want to ignore those. And they really sort of, I'll break it into 3 classes. I'm sure you could break it into many more. But sugar and starch, fats and oils, and lignocellulosics. So sugars and starches, they're refined global commodities. They're produced on large scale at competitive costs, 12 to 25 cents per pound, which, to give you some of a frame of reference, ethylene varies anywhere from 15 to 40 cents per pound. So they're in the same price range as ethylene and propylene. And they're based on carbohydrates, which are shown below. Fats and oils are, again, a refined global commodity. We're all familiar with edible oils that we purchase at the grocery store. Again, produced on similar scales with similar price breakdown to the sugars. Now, the advantage of the fats and oils, if you look at the structures, they're functionalized hydrocarbons. So you're basically taking something that has taken ethylene and oligomerized it and functionalized it and getting it at basically the same cost as ethylene. So there's certainly a lot of interest in the fats and oils as well. But then there's the real opportunity, but the real challenge, which is lignocellulosics. These are crude materials that are limited from a supply chain standpoint. They're, however, on a scale of roughly 100 gigatons at basically fuel value. So these are in huge abundance at low cost. But the challenge there is they're over-functionalized. So now you've got materials that are very difficult to work with and difficult to convert to a useful intermediate. But these are just 3 primary examples of materials that could be utilized for feedstocks. And just to kind of calibrate you on the amounts, what's shown here is ethylene and propylene amounts per year versus seed oils and carbohydrates. And what you see is that seed oils and carbohydrates are at scales that are competitive with our ethylene and propylene supply. So you could view these as really viable world-scale commodity chemicals. The challenge, of course, though, is because they're of comparable size, if we decide to use these as a significant displacement in our feedstocks, you're going to have a huge impact on the food chain. I mean, this will have a serious impact on supply of edible oils and carbohydrates. But they are realistic to view for certain applications as feedstocks, and that's really the point here. But if you can go to lignocellulosics, you have the overall best case because you're not impacting the food supply, and there are very large quantities to supply the chemical industry. The challenge there, of course, is the technical one. How do you convert those to something that you really want?
When you talk about prices, are you talking of prices now or prices after you build all these plants and you're going to drive the price of sugar up?
Well, so this is the price now, and that's the problem. So that's why when I say you're going to have an impact, if you're going to convert seed oils or carbohydrates to chemicals at a world scale, because they're of comparable scales with ethylene and propylene now, if you did that for a large-scale application, you are going to impact the price. Whereas with lignocellulosics, you have a much better opportunity there because you're talking about a much smaller fraction. You're not impacting an already existing value chain, but you're completely right. I mean, the initial applications in the seed oils or carbohydrate areas are going to be, I think, for smaller volume applications that can be built over time, but there will definitely be a price impact. But people are interested because of the advantage price at this point, and this is just, again, a historical graph to show relative price comparisons. And what you see in red is the spot price of propylene, which number one you'll see is highly volatile, and number two you'll see is for the most part higher in cost than the renewable feedstocks, or at least comparable. In green you see soybean, and at the bottom you see why there would be interest in the sugars, which is the low cost per pound of sugars. So these are competitive in price, and they are, for the most part, less volatile than ethylene, propylene, or oil and natural gas feedstocks. But again, to your point, we have to take a measured approach to the applications that we put them in because you are going to have an impact on pricing if you go to large-scale production from these. And if you look at the technologies needed here, at least from a Dow perspective, I can kind of break down how we view this, both from a technology and a market application standpoint. Conversion, thermochemical conversion, the application of a biorefinery, and then fermentation. So thermochemical, things where we can do a Dow or a chemical industry core competency, hydroformulating, hydrochlorinating, hydrogenating, epoxidizing, polymerization. These are all basically taking a refined feedstock and just doing a known catalytic conversion to make something that we know today. That's from a technology standpoint a very low risk. A biorefinery where you're taking a complex process mix, doing things like gasification, pyrolysis, fermentation, and the thermochemical and power generation, where you would build an integrated refinery based on renewable feedstocks. Well, that's a lot riskier proposal with a lot more complex technologies that have to be brought together. And really at the crux of that is fermentation as a technology that really has to be improved to make a lot of these processes competitive. And where you see the impact there is sugars and fats are very well suited to the sort of thermochemical approach. We're just going to take a refined material and we're going to convert it to things that we know how to utilize today. Lignocellulosics and sugar and starch and cellulose, however, take you more into we have to develop fermentation technology and we have to develop an integrated biorefinery approach, which brings with it more risk and a longer-term strategy. But there's more to it than just the technology part. There's the market acceptance. And really, when you look at biomass-based materials, there's sort of, in my view, three categories. The first one is exact replacement. So what do we mean by that? Well, we take a renewable feedstock and we make something that we already make today, and the advantage is it costs less. So that's one where there's almost no barrier to entry into that, and there's very low risk for the company. You're going to make something we already make. The customer's not going to see any difference, and the reason you would do it is because it's one, renewable, and two, the cost is less. So an example would be, and actually I think a significant one, biodiesel, which most of you are familiar with, is basically just taking a triglyceride, reacting it with methanol to make a fatty acid methyl ester and glycerin. Well, the biodiesel is the fatty acid methyl ester. The glycerin is a byproduct. Well, just kind of show you how fast, for an exact replacement, a market can be impacted. Dow commercially produced synthetic glycerin from the hydrolysis of epichlorohydrin. So for those that aren't familiar, that's just the chlorinated version of propylene oxide. Based on growth in biodiesel and the low cost of glycerin, we have now shut down production capacity of synthetic glycerin from epichlorohydrin. So because we can't make it at the cost, based on a growth in the based on biodiesel growth, we've shut down a commercial production. So in an exact replacement standpoint, you can have a very immediate market impact. The next one is, it takes on a little more risk, which is you're going to produce something that the customer is not going to see as any different. The consumer, I'll say. The consumer is not going to see the product as any different, but the customer will know that it's a different one. So for example, if you're selling your resin to an automobile producer, such as I guess the Studebaker shown here, the automobile manufacturer knows that they're getting a different material. Let's say you're making the foam for the seat cushion out of a renewable material. They know they're getting a different material, but the consumer, when they sit in the car, has no idea that it's a different material. So there's no barrier to entry in the consumer market. There is a barrier to the customer to understand the property cost benefit analysis. So there's some risk, but once you get through that, implementation with the customer is quite rapid because they, at the end of the day, you don't really care what's in the seat cushion for the most part. The highest risk, of course, is a new product. So this would be, some significant improvement in cost or performance. It's customer driven, and you're not typically going to drive a strategy based on renewable feedstocks in an area like that. You're going to certainly have applications that grow from that, but that's very much on the high risk end of the curve. So what I'm going to do is highlight for you a couple of things, a couple of projects in ethane activation that kind of tie into the strategy, and then one quick example of the use of biomass derived materials, and in fact specifically seed oils that we have in terms of a research effort, and then open it up to any questions, unless there are any questions now. So I think at lunch today somebody asked me about partial oxidation of ethane to ethylene. So this is how we make ethylene today. We make it from ethane by steam cracking. And basically what this technology is, for those that want to kind of avoid the whole schematic here, it's basically taking ethane, heating it up to 800 to 900 degrees in a furnace, and you get ethylene and hydrogen out the back end. You also, of course, get some methane, and you get some other hires, and you've got to do all the separations there. So you have quite a lot of capital at the back end to do the separation, and this is done on the contact time of about 1 second. So from an engineering standpoint, the front-end reactor piece is actually quite simple. The separations are more of a challenge, but this is well-known technology. This is, over 50 years old, and the technology is basically still the same today. The drivers for improving it are getting the capital down, increasing the yield of ethylene, obviously, but then even more importantly, integrating the energy, because this is a highly energy-intensive process. So an effort that was started at Dow on ethane partial oxidation. So the idea here is to use ethane and oxygen to generate your ethylene, and do that autothermally. And the goal there would be to use the heat generated from oxidation of ethane with oxygen to drive the reaction so that it doesn't require any external heat. And you run this adiabatically so that you don't have any external heating required to run the chemistry, with the goal, again, to produce ethylene. This does a number of things for you. One, it reduces the capital because you now have a much smaller reactor with much less energy intensity around that reactor because you're not having to heat it. You're using oxygen to drive that chemistry. Potentially improve the yield. You do have some trade-offs, though. You have different byproducts, which are going to have more or less value because you're not going to make exactly the same mix of products. And you're also going to have to separate and use pure oxygen versus what's used in the steam reforming. And the steam reforming, remember, you're just burning fuel on the outside, so you're using air to burn your fuel. Whereas here, you're separating pure oxygen out and feeding that into the reactor to burn your fuel. So this technology was developed in the late 90s and early in 2000. And basically takes ethane, oxygen, hydrogen in a controlled flame in the reactor, and you can actually see that. Essentially, that's glowing flame inside the reactor running between 900 and 1100 degrees to produce ethylene and other lights. Residence time is about 2 to 20 milliseconds, so this is extremely short contact time. And you can get selectivities of ethylene of about 80% and about 70% conversion of the ethane. So it's similar to the autothermal production of HCN. Very fast chemistry, small reactor. It's adiabatic, so there's no external heat transfer. It's self-controlled, and it's outside the flammability range. So it addresses a lot of the advantages that you'd want to have. Really the key issue is, can you get the selectivity that you need versus the COX that you would produce by using oxygen? And so just to kind of calibrate you on the performance, this is what, with a platinum on alumina catalyst, what you see, and you see the selectivity is much lower than a steam cracker. Or if you add hydrogen, an interesting thing happens, which is the selectivity increases dramatically. And with two later versions based on platinum 10 catalyst, with and without a hydrogen, you can actually, with hydrogen, achieve the same selectivity at the same conversion as an ethane cracker. And really the hydrogen, it turns out, is used essentially to drive the reaction by doing hydrogen combustion on the surface of the catalyst. That heat allows for the endothermic cracking of ethane to ethylene. So it's actually quite simple, and you're basically just use hydrogen as your fuel through combustion. And the key with the hydrogen is that it competes with the alkane for the surface of the catalyst to prevent over-oxidation of the alkane. So you get the heat generated from it and also protects against over-oxidation. So strong effects of the fuel-to-oxygen ratio. The catalyst formulation itself has a huge impact because of the ability to control the combustion at the surface versus oxidation of the alkane. And the hydrogen clearly has a huge impact. One of the interesting things about adiabatic reactors, though, is temperature is not an independent variable here. You don't have a temperature that you set your reactor. Basically, the amount of fuel you use and the diluent you use is what drives the temperature, so you kind of live with what comes out. In this case, it works very well, but it's not something you have direct control over. This is something that's now part of a DOE activity, working with Velocis and PNNL, really looking at designing and building a bench scale unit and then going to larger scale commercial application. The one thing that would limit this going commercial is that you lower the capital of the reactor substantially, but you still have to do separations on the back end. And it turns out, just for everybody to understand, that you spend about 60% or more of your capital on the separation to purify the ethylene. So this will overall be a lower capital process, but there's still going to be risk associated with new technology, and so that would be what would limit it. Vinyl chloride. So Dow produces 5 billion pounds per year of vinyl chloride, and that's growing at about 5% a year, and that's of world demand about 49 billion pounds. The way we do that today is we take ethane to ethylene, just like I described. We take sodium chloride to chlorine via an electrolytic cell or a chloralkali plant. Then we chlorinate ethylene to dichloroethane, and then we heat that and produce HCl and vinyl chloride. So it's actually very straightforward chemistry. The goal with our project E2V, and again, one thing you'll learn from industry if you haven't learned it yet, is that you can't have a good project unless it has a code name. So E2V is ethane to vinyl. That's what it stands for. But the goal there was, can we use ethane, convert that to vinyl chloride, and take the ethane to ethylene plant out, which is a huge capital savings if you can do that. So the vision is ethane, oxygen, HCl, convert that to vinyl chloride and water. And lab results. Well, the first studies with this used oxygen, HCl, and ethylene, and that's really where the lead was first seen, that 90% selectivity to vinyl chloride and EDC were found just feeding ethylene to the reactor. So using a catalyst at 400 degrees with oxygen HCl, we could get a very high selectivity conversion of ethylene to vinyl chloride. So the question was asked, well, what happens if we feed ethane to the reactor? With the goal being, could we convert ethane to ethylene in situ and then use that ethylene to drive the selectivity to vinyl chloride? And that's exactly what you see. And so what's shown here is that if we feed oxygen, ethane, ethylene, and HCl at a level of ethane feed that matches that produced, so essentially as a process the ethylene is fully recycled and can be taken out of the equation, we can produce 84% selectivity to vinyl chloride, EDC, and ethyl chloride, which all are viable materials in terms of the overall production of vinyl chloride, and 84% selectivity, which is very competitive. And this is based on, interestingly enough, a lanthanum-based catalyst, which was not studied initially as a catalyst by itself, because it's typically used to promote copper-based catalysts for oxidative chlorination. But a control experiment was one, and this is the reason you do a range of good control studies when you run chemistry. Lanthanum was put in just to show in the control tube that no oxidation was going to occur because it's not really a redox active metal. And of course, what you find is very high selectivity. So it's always good to do those nice control experiments. And the material is based on taking lanthanum salts, like lanthanum trichloride, reacting it with ammonium hydroxide to form a precipitate, which is then calcined to give you lanthanum oxychloride, which is in about a 30 to 120 meters squared per gram sort of surface area, depending on how you prepare it, which gives you a morphology that looks like this. When placed in the reactor, you get conversion to the chloride state under HCl. And it's interesting from the modeling and kinetic work that has gone on, the oxidation, it does not involve the lanthanum center, as one might expect, because it's not a redox active metal. But oxidation occurs on the chloride layer of the catalyst via chloroxy species that form, and do the ethane to ethylene conversion, and the energetics from that are what drive the rest of the chemistry. And I just have like 2 more slides. To sort of end, Dow has considerable efforts in biomass-derived feedstocks as well, and I mentioned some of these sort of categories. In the oil and fat area, we have an oleochemicals program, so using oils and fats as feedstocks, leveraging the supply chain and developments in the biodiesel area. And there's sort of 3 key areas. One, hydroformylation of those, which I'll talk a little bit more about. Ethanolysis, so the metathesis of those with ethylene to produce unsaturated esters for potential applications in urethanes, and epoxidation. And glycerin, which is a result of oleochemicals, biodiesel production as a feedstock for chemicals in Dow, such as epichlorohydrin or PG. Sugars and starch is something that we're following the bioethanol growth in and trying to identify the right places to take advantage of that. For example, ethanol to ethylene is a feedstock in regions where ethanol is cheap. And lignocellulosics, and that's one we're really just, they're sort of two paths there. One is just doing syngas generation, but the other is looking at growth in the biofuels area and fermentation area. But the one quick application on seed oils that I can talk about is a soybean paste polyol. Now, when I say the term polyol, what I'm referring to in Dow is that's a polyether. So the polymerization of propylene oxide or ethylene oxide would produce a polyol in Dow terminology. The goal was to take soybean oil, which is once converted to the fatty acid methyl ester, is just an unsaturated ester, and convert that to a hydroxy ester that you could polymerize to make a polyester. And that polyester, if alcohol end groups on it, could be used to make a polyurethane foam with an isocyanate. And the goal would be to match the market minimum, which is to match the current performance of Dow polyurethane foams, with the potential to grow that into enhanced areas. And to give you a sort of a feeling, this is a 3 to 4 billion pound sort of market opportunity in urethane foams. This is not a small application of seed oils, but the seed oil is a small piece of the overall material. And the process really is pretty straightforward. It's you take the seed oil, you do methanolysis to produce the fatty acid methyl ester. We hydroformulate that to produce the aldehyde, hydrogenate to the alcohol, and then polymerize that to make a polyester, diol, or triol, depending on the initiator, and then that material would then be reacted with an isocyanate to produce a polyurethane foam. And this is now moving from market development to pilot scale for implementation in urethane foams. This would be sort of that intermediate market acceptance, which is we're replacing something that's a new product, but from the customer standpoint is going to have the same performance in the same application area. It's just going to have a different feedstock. So to sort of conclude, and I'm not too far off time, hopefully, alternative feedstocks for the chemical industry are increasingly important. The challenges, though, are that breakthrough and step change processes are going to be required. Novel catalysts and reactor concepts are going to be needed. And really developing more fundamental understanding of catalytic mechanisms is going to be needed to develop these new technologies. And so a lot of the great science discussed this week is very relevant to that. But this is going to take a consistent long-term focus, and it's also going to take balancing risks in a number of feedstocks. There's not going to be one answer to what feedstock the industry is going to use. It's going to be incumbent on the industry to have technologies to apply to all the feedstocks to match the geographies that they're going to grow in. And it really is going to require significant industrial and academic partnerships to achieve this long-term research direction. And with that, I will conclude. Any questions? Well, they can't take your meal ticket away today, I guess, if they don't ask any questions. Okay. Oh.
I want to come back to this question of price. I mean, don't you really have to have some sort of self-consistent loop to estimate how much the price will change?
Sure. So we do that. So for example, in the seed oil case, we know exactly, based on projections, how much we think the price is going to change, and therefore how big of a market opportunity we have initially. So we clearly look at that because we have to have a market entry that has a consistent price structure that we understand. So you look for opportunities like in the seed oil case where we know how big we think we can grow that, and we know how much we think that's going to impact the price. And you base that on a number of things. It's not very easy to do. I mean, you're basing it on what you think production quantities of seed oils are going to be in the future, how good agriculture is going to be at improving crop yields. But you can do a pretty good estimate of what that's going to be, and that does impact the scale that you can implement these things. And you have to understand the cost sensitivity of the seed oil on your final product.
So you also talk about amortizing your investment over 20 years. How do you manage risk? I mean, you don't have any options or anything you can buy for 20 years ahead.
Well, there's less risk if you're making something you already know how to utilize. I mean, if we're going to invest $2 billion in producing ethylene, we know what the market demand for polyethylene is. I mean, but if you're doing it to produce a new material, there's a lot more risk. So you have to balance what you understand of the market and the size of the capital investment. But I'm not trying to make light of it. And, an example is, we've talked about growth in China. If you were to build an integrated Dow facility from feedstock to olefin to polyolefin you're looking at numbers of $5 to $7 billion. So you're not going to do that without understanding the risks of, and the use of the materials you're trying to make. But I think we understand polyethylene pretty well. But there is risk, and so therefore when you talk about, okay, we're going to go build that kind of investment, do you do that with a syngas-based technology that saves you somewhat on price because of the low-cost feedstock, but maybe costs you a little bit more in the capital, or do you just do it with the feedstock you already know and understand? Well, if the costs were equal, you do it with the feedstock you already understand, as long as you feel like you're going to have access to that feedstock in the future. And that's really the challenge. Is there's more and more competition over ethane and oil. The costs are very volatile. What's the risk of going away from those feedstocks versus the potential risk of developing new technologies? And it's not an easy solution. And that's why I think you don't see anyone implementing the technology yet. MTO is going to happen, but somebody's going to have to be first. And at those kind of dollar investments, it's not an easy step to make that decision.
The ethane partial oxidation pathway looks very attractive in your case. I wonder if you have any ideas or at least projections what the cost of that will be relative to the energy cost in particular, but what would the cost
I can't give you an exact number. It's definitely a savings on both energy and capital, but again, the challenge there is that from the estimates that have been done, the overall capital is certainly lower, but the bulk of the capital isn't affected. The bulk of the capital, which is the ethylene purification stream, is not. So again, it's one of those the constant challenges we have in industry, that the overall capital is going to be somewhat less. And I can't give you an exact number, but if the bulk of the capital is in the separations, you can kind of get a feel for it. So do you take the gamble on something that's going to save you 10, 20% in capital versus do new technology? And so I think those kind of things will happen, but they will happen when they need to happen, as the market will accept the risk. So it's not going to be an immediate entry. If you could reduce the capital by 30 to 40%, this would be sort of an immediate implementation.
I also wonder if there was any significance to using a Studebaker as an example, since they're no longer in business.
Yeah, there actually was a reason for that. Actually, that's that's very good observant. Yeah.
Okay, I have two questions. The first one is concerning on the natural gas conversion, direct conversion. Now there are different processes. The first one is OCM.
Right.
Then there also aromatics.
Right.
Then also the low temperature to methanol.
Right.
What is your idea? Which perhaps is promising process for in the future? This is first one.
Well,
then another one is you also talked about the natural gas to syngas, also coal to syngas. It's really low. The coal is short of the hydrogen,
right.
But the natural gas is rich of hydrogen.
Right.
Do you think it's also necessary? Also, it's very important to do something together, combine the natural gas and coal.
That's a very good point. And certainly those are
to
the
do
things
the
you have to
combine and
consider.
refining, also reforming, also such as things.
No, that's a very good point. And you clearly want to take advantage of the high quality hydrogen that you produce there. And there are ways to integrate those processes to potentially get you to a better answer. I mean, there is, you're familiar with the coal chemistry, but that clearly is the big issue, which is just that you're hydrogen deficient and you're producing a lot of CO2 and there's a lot of mass involved. Anything you could do to improve that and coupling that with the more hydrogen-rich streams is a possibility. But then that takes you into having to be in a location where you have access to all the different options. And so if anything that points to, I think it's that we have to understand that each geography is going to have a completely different set of demands, and the optimum process is going to be different for each geography. And that's sort of a different mindset. I mean, if you look at Dow today, we have ethane crackers and we have naphtha crackers, or we have flex crackers that do both, but it's pretty much the same technology. And we know when we go to another geography how to deal with that. But when you go to these options, I think like you just pointed out, based on the feedstock, you're going to have to be a lot more creative in each geography with having a different set of options. And biomass is another. I mean, biomass is another issue where you end up being hydrogen deficient again. And how do you address that, right? So it's a very good point. Now, you asked a much harder question to start, especially since I haven't seen the results from your lab, which I think are going to be talked about tomorrow on methane activation. But if you ask for my opinion, the obvious goal is to do the direct methods. So if you could do oxidative coupling of methane to ethylene, that's going to be, in my mind, the lowest capital option that's going to have the most potential. But personally, I don't see an approach at this point that gets you out of doing gas phase radical chemistry, so I don't really see a way to improve the selectivity to where it needs to be. I think it's going to require some fundamental different processing or catalytic chemistry to prevent the chemistry being driven by just gas phase methyl radical coupling. Now on the aromatic side, I think there's a lot of potential there. For a company like Dow, the real challenge then is how strategic is benzene as an investment versus olefins, right? Because I mean, in that case, you're taking methane to aromatics, and I think that as a way to make money from methane, it makes a lot of sense. If we can take a cheap natural gas field and convert that to benzene or aromatics and ship those and utilize those, it makes a lot of sense. But as a company like Dow, we're going to have to judge the investment there versus investment in producing ethylene somehow, and there may not, you have to prioritize those. So I think there's real potential in that chemistry, and maybe even coupling the aromatic with olefins to produce higher materials like styrenics and things are things to think about too. So there might be some really unique catalytic processes that could be developed there.
Could you say something more about the future about the biodiesel and bio-based something? I mean, because I think, yeah, absolutely, as you said, we will have someday that all of the the oil will be used up, and right, so
you're just so that I understand what you're asking. Do I think that we're going to have bio feedstocks for fuels as a viable? Do you mean for fuels or for chemicals?
Both.
I
would say, I would like to say both, because you can, I mean, also, I mean, do you know some policy of the U.S.?
Sure. Well, let's just talk about the fuels one for a minute, because this is actually a good conversation topic for later too. Corn to ethanol in the U.S. As a fuel makes very little sense. Just so that we're all sort of on the same page. It makes a lot of sense in Brazil, where the cost of production of ethanol from cane is more efficient and more cost effective. Now, we balance that by putting duties on imports of ethanol and subsidies for the use of ethanol to make that cost competitive. But that being said, that's from fermentation of sugars. So where the real opportunity is, in my mind, is in fermentation of cellulosic. So if you could do that, and you can make ethanol or butanol from cellulose, then that's a real viable feedstock, both for the chemical industry and for fuels. I mean, the reality is you can't meet the demands of fuel use in the U.S. with corn. There's no way you'll ever be able to do that. You could displace a certain percentage, and that's what's going to happen. And I think oxygenates and fuels will be where you see that. But you're not going to be able to meet the demands of the full demands of the industry, the fuel industry. And therefore, it's going to have limited application. But there are going to be places where it makes sense, like in Brazil. And in fact, Dow has announced that we're looking at investing in plants to convert ethanol to ethylene and ethylene to products because of the low-cost ethanol feedstock there. There are going to be cases where it makes sense. And the advantage of ethanol to feedstocks from a chemical company perspective is it allows you to completely decouple yourself from an ethane cracker. So where you would have to spend billions of dollars of investment, you can now go and do a simple dehydration of ethanol and make what you want in a certain geography to grow the market there. So, I mean, there are a lot of reasons why it makes a lot of sense, but it really still requires the ethanol to be competitive in price. Now, fermentation to ethanol or butanol or other materials for fuels, I think, is that's where I would see an investment that makes sense for the fuel companies, and clearly they are doing that. I mean, you can't pick up a newspaper today without seeing BP or others talking about fermentation, DuPont as well. I think that's a ways off, though, before that's competitive. Biodiesel is really the same issue as ethanol in my mind. I mean, biodiesel is going to have limited acceptance for fuels. Again, the volumes really aren't going to be there. It's going to have an impact, though. And from a chemical company perspective, the way I look at ethanol and biodiesel is what can we do to take advantage of those being more available to make new products and make money from it? And there are ways we can. It may not be that biodiesel takes over fuels, but it could be that glycerin price drops substantially, so we have to change, one, how we make glycerin or how we utilize it. So it does impact the industry, but whether that's going to grow to displace gasoline in the near future, I don't see that being the case, except for the potentially the cellulosic fermentation. But again, that's longer term answer. Does that get at what you're asking?
Thank you. First of all, I welcome the opportunity to be here today. I just moved to Santa Barbara about 5 months ago. I was with Kodak for 25 years. While I was with Kodak, I managed part of the health business that focused on cardiology that was primarily a business based in Japan, the US, and Western Europe. I managed the camera business, which included reloadable film cameras, single-use cameras, batteries, and the beginnings of our digital camera business. The consumer output, photographic paper, and photo finishing systems businesses, and finally the professional imaging business. Now, what's interesting about the health business and the professional imaging business is that both of them are over 50% digital now at this point, and the consumer business, which I was last with, is roughly about 50% as well. For the last several years, I lived in Shanghai, China, and just moved here earlier this year. And when I was in Shanghai, I managed Kodak's business operations, including manufacturing, R&D investments, et cetera, across all of Asia. So I'm going to talk to you about global opportunities and challenges, and a lot about agility. And as technologists, whether you're in academia, whether you're in companies, whether you're with government organizations, you will have partners. And they will be partners that will be across a myriad of boundaries. Intellectual boundaries, boundaries of disciplines, of geographies, of markets. And it's important to understand the challenges and the opportunities in context. And that's what I'm going to talk to you today about. Kodak is a company, as Gary indicated, in transformation. This was a stable company when I joined it in 1980. It was a very profitable company. It was primarily a North American company. It called itself a global company. It was an American company that just did very well everywhere in the world. It was a dominant company, other than in Japan. And it led in market share in virtually all of the businesses that it participated in. But the world has changed, competition came, and changes in technology as well as market participants. So I'm going to talk about Kodak's strategy for success, how China fit in it, and this became a company rallying cry. And by the way, if there was a representative from GE or other major companies, they would talk about China as a must-win. And I'll talk about China because it's on every strategic roadmap for every global company. If you're going to be number one or number two, you have to win in China. And meanwhile, there are a lot of Chinese companies that have the same dreams and desires to be global one and number two. I'll talk about the actions then that were led within the company to position ourselves in China, give you a sense of investments, how it has been a global effort with teams continuing to work, and how China has become a critical platform for development and capability within Kodak, and the learnings associated with that. And I'll talk about some of the mistakes that we certainly made along the way. The company's priorities then, maximize the traditional business. As of last year, Kodak actually had revenues. It's a $14.5 billion company. More than half of the revenues now are associated with digital. The profitability is associated with the traditional film and paper business. That's a very mature, very profitable business, and actually the paper business continues to grow, particularly in emerging markets. The film business, though highly profitable, of course, is declining, but very highly profitable. Aggressively growing digital businesses. When I was with the commercial businesses, we crossed the digital chasm. When I was with the health business, we crossed the digital chasm, meaning the workflows of our customers went digital. So whether the input was a digital file or whether it was an optical file, it was digital as soon as it was scanned. And therefore, it had the opportunities to be sharpened, manipulated, improved, and printed or stored in a variety of factors. The digital businesses now in health are profitable and the commercial businesses are profitable. Consumer continues to be a challenge for Kodak. So the company's business model, if you look at the stock price today and you look at the stock history, it reflects these technological changes and the profitabilities associated with that. So very frankly, I and every other manager of the company spent a tremendous amount of time ripping out costs. And that affected how we approached suppliers, how we did designs, how we approached capital programs, certainly how we led our manufacturing processes to drive out waste, how we took out waste in our marketing practices, how we approached our services. Changing the business model to be future-oriented is a critical element. And finally, a fundamental was winning, number one or number two in every key emerging market. And that certainly is true in China, certainly true in India, certainly true in Russia. It is still a question in Indonesia. That's a market where where Kodak continues to struggle in some of the market segments, but in others we lead. Now, China, what a must win. And this was an individual who became our chairman, our CEO, and back in 1993 was a person by the name of George Fisher. George Fisher was an individual who had been CEO of Motorola. He in fact, was the chairman, he was leader of Motorola that after Tiananmen Square made a big investment in China that was controversial in the States. It was controversial in the Western press. When he came to Kodak in 1993, he challenged the company. How can we be number one in the world without being number one in China? And the reasons are the market opportunity, 1.3 billion people. Today, camera ownership across China is still only 24% of households. We knew in 1993, although it was often 7 or 8, depending in size and market segment, that it would eventually be the number one imaging market in the world. Today it's number 2, or it could be number 3 behind Japan, depending on the material you look at. Commercial printing, today number 7. It'll be number 2 by 2012. It will be the biggest health market in the world. So you can't stand back and say from a market opportunity, I'm not going to win in China. And I'll talk about a couple other companies and how they've had to flex their model as the laws within China have changed. The talents and capabilities within China, and I'm focusing on China, but then the company too has opportunities in other markets such as India. But talents in terms of not only manufacturing, but innovation, development, marketing, the talents and capabilities. And when I look at the capabilities that we've established within Kodak relative to Six Sigma knowledge, lean manufacturing, lean design, software development, chemical process development, it has become the global platform for many of our capabilities in the world. Certainly innovation. One of the things that is important for researchers to recognize that as you work, the platforms for excellence and specific knowledge will shift. And so, for instance, the platform for specific research will be based within a company in Munich, and this is true, for instance, for GE. In Munich, they'll have one in Bangalore, they'll have one in Shanghai, and they'll have one in the States. The same thing for Kodak and other companies. The critical knowledge base shifts, and so the knowledge of where capabilities are fundamental. Certainly manufacturing, and it's key to know in innovation in manufacturing, people sometimes look at the press and assume that it's less complex manufacturing. China has certainly had roots in lower capability manufacturing. It has a myriad now, a stream of low-cost manufacturing, simple products for high volume. It has capability for mid to low volume, highly complex systems products. In terms of R&D, growing capability in both in innovation as well as pure research invention. And that is where the Chinese government clearly wants to place investments, because low-cost manufacturing will move very quickly. Somebody will always make it cheaper. But the future opportunity for an economy is based on innovation and invention. And that is the future and certainly the emphasis of the Chinese government. Sourcing, of course, is critical. Most Western European and American companies can move to China for sourcing of critical parts and have 50% of cost out before the hard work starts. So it's a critical endeavor to think about the capabilities and margin opportunity that you have with establishing new capabilities in China. Brand is critical. When people ask about IPR, intellectual property rights, so much of it is about the value of the brand that you establish and the differentiation you're able to drive with your brand and therefore protect it, at the same time, obviously, that others will begin to, in a sense, copy that. And finally, it's important wherever you do business is to understand how business is done. In China, it means you work with the government officials at the national level, you work with them at the provincial level, you work with them at the local level. And one of the things that I'll note is that within China, it's important to know at times, the last point, or the second to last point, that there's a difference between laws and interpretation. Meaning that within China, people would ask me about working with China, and I would say it was the most free market, the most practical communist country that I've ever worked in. Meaning that we spent a lot of time working with the government. What were the plans? What were the opportunities? And therefore, we would work out pragmatic solutions. It also meant that Kodak, as a multinational company, spent a lot of time inputting into the future, for instance, around the issue of registration of new chemicals, as we were doing more development for chemical process. It was through some of the Kodak products that, in fact, the modification of the process was done. We've spent a lot of time with the government on new environmental policy, new environmental statutes, and the reason is the infrastructure across China varies tremendously if you're versus Shanghai, for instance, Wulamuchi. So within China, there's a tremendous difference, and this is certainly highlighted in the press and economics, personal economics of the 1.3 billion people. 800 million people are tied at this point to agriculture. That's often missed when people think about China. When you look at economics, there's a tremendous amount of discretionary income, particularly for young professional people living in the cities, because they share often an apartment with their parents. So as a result, and I'll talk about brand sophistication and where income is spent, there's a tremendous interest in luxury goods, in consumer goods, the market for those products driven by a lot of opportunity and a desire, for instance, for cars, and I'll highlight durable goods, cars, apartments, etc. Now, the infrastructure of China greatly varies. In 1994, when I started going to China, we started looking at putting plants there. We looked at, for instance, Chengdu. The logistics and infrastructure didn't exist at that time. Today, I would have no worries about putting a plant in mid-China or West China. But at that point, we made our decisions to, in fact, base our plant, base our capabilities along the coast. A lot of that was driven by logistics. Today, there's about 1.4, if you look at the infrastructure on roadways, China is approaching most percentage-wise, most of the larger, more developed markets, and that will continue to be investment because even by 2010, only 5% of the population will have cars. So tremendous opportunity, tremendous change constantly in infrastructure. Across China, although modern Chinese, Mandarin, of course, is the established language, modern Chinese meaning ping is used, but dialects, and as somebody who has tried to learn Mandarin, I can tell you that for every word, depending on the tonality, there are at least 4 meanings, and in some parts of the country, 16. And so it's a very difficult, and whenever anyone has asked me whether I speak Chinese, I always use the word idian, which means a little bit. I think I will spend my lifetime always speaking idian, despite best efforts. I've mentioned laws and interpretation in terms of this practical opportunity of working with the government as a partner, and every successful company that is operating within China does that. A lot of focus on governmental relations. They have a strategic plan for the country, for the opportunity, and it's an important part to participate in that. And finally, retail development. And this is critical as you look at the products you're developing, how they go to market, what type of opportunity. And just in the last couple years, and I'll highlight Avon Products. Avon Products was not allowed to distribute its products through home parties, which is primarily the way that Amway and Avon has distributed their products around the world. They had to open up shops, boutiques, and Avon opened 5,000 boutiques. They have been allowed, because of changes in retail law now, to in fact have home distributors, home promoters. And they in fact are hiring over 100,000 promoters to promote the sale of their product. So Chinese laws, the interpretation is changing, providing tremendous new opportunities. The consumer tiers, and this shows a difference. The first tier, there 27 leading cities. These are several million people. High income, relatively high brand sophistication. So again, that interest in the brand. And per capita income about $1,050 a year. So that's about 87 million people within China. The next section is the second tier city, and Dalian is I would always put it in tier 1. I've seen it in tier 2 because it is a very sophisticated city. But tier 2, still lower disposable income slightly, but increasing brand sophistication. And finally, the large mass of where most people live would be in about 400 tertiary cities. These are still around 50,000 people. And then the rural areas. And so, that's where you have lesser disposable income, less brand sophistication or awareness, and lower per capita income. And as a consumer marketer, you have to do different things, both from an infrastructure vantage point, from a category awareness vantage point, and certainly from a retailing and merchandising effort across that hierarchy. Now, just some images coming from an imaging company. I love images. The upper left-hand corner is Nanjing Road, which is one of the most sophisticated and always busy parts of Shanghai. It's busy at 7 in the morning, it's busy at midnight, and it's one of the big shopping areas. The image on the right is the new Louis Vuitton store in Shanghai, very successful, very expensive prices. And you will find every big luxury make in the big cities in China. The lower left-hand corner is in a secondary city that's a Kodak Express, and you can see that it looks like any other camera store, imaging store anywhere in the world. The lower right is Jialafu, Carrefour, and Carrefour has been very successful in China with very competitive prices and very well accepted. The next store, the upper left-hand shot was taken in a secondary city, but frankly, it's an outlet. It's a store. You would find this in the streets of Shanghai. You would find it in Wulamuchi. You would find it anywhere. The woman to the right in the red suit is Andrea Zhang, who heads Avon Products, and she was the one that decided that Avon could not be successful without getting into China, without winning in China, and they're establishing themselves as a value-oriented cosmetics opportunity. And that's a company, again, that had the obstacle of not being able to use their common go-to-market capability that they had used successfully elsewhere in the world. And now with changes in the law, they'll be able to. Lower left-hand corner is a Kodak Express in a rural area. You can see it's more really like a kiosk. And the one on the right, which is a little grim, is a retail operation in a very rural area. So tremendous differences in retail outlets, retail merchandising, retail sophistication, and the hierarchy that it takes to get your products to market. Now, this may be a little bit hard from the back to see, but this is a key chart. 2004 was the last time that Gallup poll did this, but I think it's a fascinating chart to show the changes of durable goods ownership from 1994 to 2004. And you'll see that color TVs is now above 80%. 80% of the population has a color TV. That's up 50%, or that's up from 40% 10 years before. Landlines are up 6 times versus what they were in 1994. Now, cell phone ownership, it highlights that at 48%, you need to know that China is the second biggest cell market in the world and certainly will be #1 very shortly. It's also one of the largest internet markets in the world. Now, PC ownership isn't as high, although many people use a PC at the office and not so much at home. But it's important to highlight it's got that cameras at 24%, up from 15%, just tremendous discretionary income, upward mobility, and more interest and opportunity in purchasing consumer goods. Now, camera ownership, you can see, in fact, this difference that I highlighted before. In the Tier 1 cities, a lot of digital cameras. A lot of digital cameras, a lot high camera involvement. 57% of the households have cameras of some type. Now, recognize that in China, like elsewhere too, mobile phones now have reasonable cameras built into the phone itself. In the second tier, it's about 40%, and then in the third tier, only 7%. So what is being done, obviously, in the second tier in terms of encouraging involvement of the category, encouraging distribution, would be different than in the first tier with more film cameras, but a lot of digital cameras going into Tier 2, and then in the third tier, making very low-cost cameras available to consumers. So in 1993, 1994, we were 3rd or 4th in market share in all of the segments, and yet we knew that China was going to be the biggest opportunity in the world. We had 3 offices, we had 30 people. That was not a strategy to win. So we as a company defined a strategy that we would bring the best of the world to China, and we would bring the best of China to the world. And that has spelled out what has been a consistent strategy. Tactics have changed, but that's been a consistent strategy of taking Kodak's management practices, a commitment to innovation. And as a part, one of the things in management practices you'll see is that Kodak has the same 6 values around the world. We talk about global values, but local characteristics. It's understanding that those values mean slightly different things and require different behaviors locally. We were committed to innovation, and as we partnered with the government, and I'll speak a little bit more about that, we indicated we would first of all bring world-class technology, product technology, process technology. We would invest it, and in fact we would have world-class Six Sigma, best in the world capability, and then take that capability and support the world. The same quality, this relates to the brand, obviously, it relates to the customer satisfaction that we would expect. Being a model citizen, employer of choice, it is absolutely a war for talent in China. Most companies have 25 to 30% turnover a year. Kodak had about 10, and it's because we constantly worked on it. A long-term commitment to China for companies that are considering going to China because it's easier to buy versus make are not going to be supported by the government. It's about being a part of China's future is what being part of the solution is there. And then finally, being an industry and technology leader. So this same chart was developed 10 years ago and still hangs in many places, and we would go back and point and make decisions against that strategy. So today, Kodak is a major investor, and I'll highlight that we've invested close to $2 billion in manufacturing assets, including about $1.5 billion in a world-class coating capability in Xiamen. Manufacturer both of digital as well as optical systems, chemical products, and not only for China, not only for Asia, but for the world. We're a very large exporter, particularly in the Xiamen area. Development today is focused both on primarily digital systems in the health area, which would be related to PACS. It's related to digital radiography, digital computed radiography, and it's also for some film systems. It's for commercial systems for printing, And it's also on the software side for kiosks, and for instance, we develop a lot of compression algorithms in Shanghai that are used in Hollywood. Retail leader and partner, I'll highlight the investment in the market that we've done in terms of development of brand, but also in retail partnerships. The market leader, again, this has positioned us as number 1 or number 2 in all of the markets that we're in China. Leading exporter, and in fact, again and again, we've been highlighted by the government, by the press, by consumers as a model company, and that's certainly the way that we want to continue. Now, in 1995, we went to the government with a very controversial plan, and that was there was a Chinese industry, a state-owned industry associated with the sensitizing of photographic materials. There were 7 major companies in that, the largest being Lucky Film. We offered to the government, and it was accepted in 1997, that we would purchase, and we were allowed to purchase 5 of the 7 companies, rationalize those, and we then at the same time built this world-class coating capability in Xiamen and chemical manufacturing capability in Wuxi. The other 2 companies, one which was the Shanghai Photographic Material Company, their business license was changed, and I'll tell you what we got for all of this, was their business license was changed. Lucky was left alone, and I'll come back to Lucky later. For that, Kodak got a 4-year head start in terms of other foreign manufacturers in terms of their ability to sell in country, meaning you could manufacture in country, but you couldn't sell in country. So our proposal was that we would have a head start of the foreign manufacturers in the Chinese market if we rationalized what then was a sick industry, and we would bring world-class technology to this industry, better solutions to the Chinese consumers, et cetera. You can imagine that this was viewed both with pro and con reaction in China and elsewhere. It was accepted, and we moved ahead. Fuji, which is our primary competitor around the world, was not happy about that result. In 1999, we started producing film and paper, initially for the Chinese market, but then for the world. In 1998, we opened up our first development center focused on consumer opportunities, consumer and commercial in Shanghai. In 2000, manufacturing single-use cameras in Xiamen. We started digital camera manufacturing in 2001, Shanghai. The next was digital output for primarily consumer and professional opportunities in Shanghai. And in 2003, we came back to the government with a proposal that was accepted because Lucky was interested at that time in having an investor. But they wanted an investor that would leave them as an independent company, an independent Chinese company. They have a fabulous reputation within China, and we were willing to live with those terms. We have only 1 seat on their board, and we own 20% of the company. So they continue to be a leading Chinese manufacturer. In 2004, we opened both a development center focused on the development of digital technology for the health field, as well as manufacturing capabilities. And again, they're designing products and systems that are utilized around the world. In 2004, we did the same thing in the commercial commercial area. And last year, we actually moved some of the capabilities we had developed on the optical side to move into the digital media manufacturing capability in Xiamen. And also, they're in the process of bringing up a computer-to-plate printing plate capability. So, in terms of market acceptance then, one of the things we had to build was interest in photography, because very frankly in 1993 we had low household, 20% of the households were active in photography. So huge opportunity. So tremendous investment in showing the category, getting people active in the category, building distribution across the country, having events and promotions that engaged people in photography, building the brand presence, and then finally establishing, obviously, systems and service. One of the things that we also did through that was we started developing more and more of our products to specifically meet the Chinese consumer preference, certainly in the medical area, the health practitioners' preferences, et cetera. That model is actually launching digital cameras that we designed in China, manufactured in China, and they're sold through the world. One of the things we did relative to the market investment was establish retail presence. There were two types of stores: a full capability photo store that had not only film, but then eventually digital cameras, printing, et cetera, was a Kodak Express. Now, they're all independently owned. We also opened local kiosks that wouldn't have development in printing. Those were photoshops. You can see there's a combined about 15,000 outlet, which is the largest retail presence under one name across China. So to give you an idea, going back to there's no one set of retail, you can see the upper left Kodak Express, that one is in Beijing. The one to the right is, upper right, is in a secondary city. The one down below on the left is in Qingdao. And the one on the right is in a western, more rural city. So fitting local retail, again, all independently owned, but supported. One of the programs that we did was Be Your Own Boss. And for the equivalent of $10,000 US, you could purchase a mini lab, receive the signage, receive the support, including all of the materials, and be in business. So we would highlight a motor scooter, buy a motor scooter, or become your own boss. And this was a very popular solution for people to become an entrepreneur. The war for talent in China. This is about people excellence. There's a Chinese proverb that talks about 1 year of prosperity, grow wheat; for 10 years of prosperity, grow trees; and for 100 years of prosperity, grow people. And that has been fundamental. Going back to this issues about teams and recognizing capabilities and how to utilize them, this is a key proverb that we've held to. These are the 6 values that I highlighted, and certainly trust, integrity, credibility, respect for the individual, continuous improvement, rewards, and celebration. True across the world, but it's interesting that you need to understand what those words mean. And one of the things we did last year within China is to have a lot of focus groups with employees about what each one of those meant. And it was tremendously learning for all of us. For instance, the first one in trust, which was a value that in the US, if you say, I trust you, it means if I tell you a secret, you won't tell anybody. In China, the feedback our employees gave us is, if I tell you a secret, I expect you to do something to help me. It doesn't mean that it stays a secret, by the way, because I have to take the responsibility for advocating for that individual. So when I first went to China, one of the things that I learned was a secret's not a secret. And in fact, when people ask you questions, it's data gathering, it's not judgment. I've never been asked so many times how much I weigh. I've never been asked so many times how much money I make. It's data gathering, it's not judgment, and you have to understand that. So it's important to understand behind, for instance, rewards and celebration. One of the things we found very meaningful to our employees was as they obtained certifications and training, and for instance became black belts, Six Sigma black belts, we did a lot of celebration around that. We did a lot of celebration that involved families. That was very important for people to understand how the company linked to the future of China, how they were important to the company, and that we involved them. So a lot of opportunity around Staff Club to do that. Now, capability development. I highlighted the fact, very mobile workforce, very desirable workforce, particularly for individuals that work for multinational companies, and state-owned enterprises often get bad press in the West. State-owned enterprises vary tremendously in capability, in new thinking, in sophistication, and there's a lot of hiring by the SOEs of very bright, very talented individuals. So one of the things that we did was we communicated again over and over and over again the importance of the strategy, Kodak strategy, the importance of the local teams, what they were doing, how this research project was an important element of the strategy, how this lean manufacturing, how this Kaizen would improve the customer experience. Because it was important to remind people how they, in fact, were part of the company and making a big contribution to the company. Going back to Kodak, we were in changing markets, and that was true in China. China has gone consumer digital much faster than we anticipated. So Bob's comment about making big asset judgments, and you put a couple $1 billion, $1 billion here and $1 billion there, it's a lot of money. And you have to make those asset judgments with the best information you have, and then be able to think through contingencies of how you're going to use them if it doesn't play out the way that you wanted it to. And one of the things you have to know is it won't go the way that you fully expect it to be. So agility in terms of technology use, in terms of technology choice, in terms of asset utilization, in terms of capabilities was key. One of the things that we held to, not only in China but around the world, but specifically in China, was what we called the 4 greats. It meant that we hired great people. It meant that we gave those people great assignments. And we spent a lot of time on keeping them in key assignments where they learned new skills, and that they could see this new skill obtainment as important to the company, important to our success in China. We talked about great moves, how we could give somebody, for instance, who had been in the research or development organization experience in manufacturing or in marketing. One of the efforts that we've done around third-tier marketing is to, in fact, take teams that are very strong in manufacturing using lean manufacturing principles and apply it to local marketing. And that's been highly helpful to the marketing and sales teams, and it's given a brand new perspective to the manufacturing guys who couldn't understand why they just didn't sell the stuff that was made. So it's been very helpful to build business context. And then finally, great feedback. And helping our employees grow through constructive feedback and having them give feedback to their bosses and supervision. One of the key things in a part of this is a tremendous focus on the localization of management talent. And so we've focused on leadership development and employee development, because one of the things that Kodak needs is, with every multinational, is the future of the companies. When you look at whether you're a Danish company or whether you're an American company or a Canadian company, look at where your sales are coming from and will from the future. The talent has to come from Asia. It has to come from Asia, because that's where the sales for those companies will be. So a key role for us, not only for the leadership of Asia, but the leadership of the corporation had to be there. Core knowledge, and this obviously was relative to their specific discipline or specific role, but it was also in Six Sigma, in lean manufacturing. And then finally, winning an inclusive culture, it was recognizing, celebrating, and leveraging differences. And people have said to me, but China's one country, but there are tremendous differences within China in terms of culture and dialect. And as a result, we spent a lot of time on looking at how we establish diverse teams to maximize contributions. The mission and deliverables have to be clear, steady communications, very clear accountability, respectful relationships, performance-based. We would always say no divas, meaning no one's irreplaceable, no one is above the norms of the team. We have to balance the teams with knowledge and experience and skills. We need to value the differences, and the team then would be winning and inclusive. And we found that this actually, we wondered how this focus would be accepted in places, not only China, India, etc., very well, because most people don't recognize outside of Asia the breadth of diversity within Asia and within China and within India, etc. As a result, Kodak has continued to be highlighted as one of the companies to work for, one of the companies to be with. And the learnings have been this focus on key strategy and measures, communication and alignment, using the best-in-class practices, which now often for the world come from China, come from Asia, and bringing the best of the world to China, but bringing the best of the China to the world. The next one, patience, is anytime you set out on a journey, which becoming #1 in China was a journey for us. And in fact, if you highlight, you saw a face of a monkey king early in my slides. That was chosen specifically. In the 14th century, there was a book written called Journey to the West, and it's about the Monkey King. Now, the Monkey King is the symbolism of transformation and agility. The Monkey King was a monkey, and he was a king, but he had capabilities to transform himself in about 70+ different permutations, and he could somersault in the sky. He had a variety of, he could change his shape, he could do tremendous things, much better than Harry Potter. Well, the Monkey King also had to change because he was a mischievous monkey, and he got into trouble, and at one point, actually, he was very haughty, and at one point, he stole sacred peaches. So he was imprisoned for 500 years. But he was given a reprieve. He had initially this neck brace that he would be zapped if, in fact, he was a bad monkey. But he was given the task of going with the priest to India to bring back the sacred scriptures, which became the foundations of Buddhism. So this story goes on about the Monkey King learning to use his capabilities and transform himself in an agile way and fight off serpents in the skies and dragons. And he, in fact, helped his team, which was highly diverse, included a pig, to bring back the scriptures to China. And for that, he was freed, and he was an elevated monkey. So when you think about the symbolism of change and transformation, it's all in that book, The Journey to the West, which is a very, very famous book within China. But patience is a key thing. I spent a lot of time trying to tell Rochester to be patient with our progress in China, but it's all about accountability. So with that, I will end. And again, although I focused on China, I used it as a focus that global teams, global initiatives, understanding the context of how people around the world come together to really make something happen. So with that, I'll open it up to questions. Any questions, or are you ready for break? Is it okay?
We talked about other companies having a high turnover rate of 25% and you having one of 10. Did that mean 25% of the employees were fired in other countries, or 25% of the employees left for better jobs because they're really good employees? In your case, you keep those 25%? And what do you mean that you work on it when you say that?
Well, first of all, there are so many opportunities for capable individuals in China that there's great turnover. And also, there's a lot of enthusiasm about having multiple companies, multiple multinational companies on your resume. And so people go to a company and expect only to stay 2 to 3 years. And you can guarantee that will happen if you're not constantly giving them new assignments with greater opportunity and greater learning. And so we used what I called the 4 greats as really a way of getting good people and keeping good people, and knowing that if we invested in them, they would feel more compulsion to staying with Kodak. And when I met with the other, my equivalents of other multinational companies, this was the #1 topic we always talked about. Because they're not only our opportunities if you're 26 years old, for instance, and with a technical background or a business background, to go from one multinational company to a state-owned enterprise or to another multinational company, but also to start your own business. And I would often have employees say, well, I'd like to go and start a software company, and I might be Bill Gates, the Bill Gates of China. And you know, they might be. And if it didn't work out, they in fact could join another multinational. There's a scarcity of certain talents, particularly as China booms, for purchasing people, for people with very critical financial capabilities like treasury, attorneys that have that know the Chinese law but also know a lot of American law. It's very difficult to hire PRC-born and raised managers with tremendous experience because former development didn't give people broad Western management experiences. So there's a lot of interest now in gaining those, and every business school in the US and in England and Australia is trying to open up a program there. So it's a constant focus, and what we would do is try to plan on hiring in anticipation of attrition. But most companies run 25 to 30%, and we work very hard to keep ours to 10%. There are so many opportunities for people that you know, there's much more demand than supply. Other questions? Yes, Alec? Oh.
I wanted to kind of refocus this point you just made and maybe invite Bob to comment on this as well in terms of the opportunities for technically trained people like those attending this summer school. What's the scenario, the scene look like in China these days for people with chemical background and technical background?
Well, I mean, there's, from the chemical perspective, I mean, there are huge opportunities. I mean, you know, she mentioned GE as well as Dow and other companies are making huge investments there. And thank you. They're making huge investments there. Right. And the same issues with turnover, with attracting top talent. You know, having a brand recognition like a Kodak or a Dow or a GE helps with that. But that doesn't keep someone. That gets somebody in the door. And so I think there are huge opportunities. You know, some companies are growing at different rates in terms of their investment, but they're, from a chemistry, a process standpoint, a manufacturing standpoint, huge investments in moving into the future. So huge opportunities. Yep.
I also had a question. First, is that a Kodak camera picture of the Great Wall?
No, I took that one. I can give you a picture of it if you want.
Anyway, what do you think are the prospects for some of our students to be employed in China?
Well,
I mean, American may be even born and going there.
The question was opportunities for students in the future in China. China will increasingly become a tremendous opportunity for individuals that have the interest in working there. And that's not just American-born Chinese, but American-born, period. And I would encourage any person at this point that is interested in business, interested in technology, interested in manufacturing, interested in marketing, spend several years in China. You know, I'll be political for a moment. It will be the superpower in our lifetimes. It's important for people to understand China. And the opportunity, the enthusiasm, the resourcefulness, you can tell I'm very, very positive about China and its future. There's no turning back in terms of you know, political concerns in the past. Tremendous opportunity, and companies like Dow, like Kodak, like BASF, like GE are banking on the future of China for market reasons, for manufacturing, for development. All of the capabilities are there and can be developed.
I just have one quick question on the management pipeline. So when Kodak first went there, how did you address that gap in, you know, in experience and management abilities in the first few years?
First few years, and this is something that, again, I could look at many companies and they vary today. And I'll take an extreme. Philips today is still a Dutch company operating in China. Then you have other companies that are all Chinese. And it's been interesting because our Chinese employees would say, we want a certain balance of expatriate thinking and experience. So when we started on this grand plan, on this grand journey, virtually all the leadership was non-Chinese. It was American, it was Brazilian, it was French, it was Australian, it was from everywhere in the world. But the goal was to increasingly have it led and therefore owned by the Chinese. And when you look at Kodak's leadership team today, I mean, that was one of my goals, and it's over 95% Chinese today. And in fact, they split my position when I left the company. North Asia is now headed by a Chinese individual. And so it's very key for a company to have that goal and have that commitment. But to your comment, there were specific capabilities, purchasing being one of them, that we knew there would be a longer lag time to having the right global experience, which meant that we had in HR, the individual who heads Kodak China for HR, human resources, spent a short-term assignment in the States to get more experience. She's now in Australia getting experience. So it's important to have individuals that are global in their thinking and experience, heading China, then heading Asia, and then heading the world. But we've had to take it step by step, but that has to be a constant focus. We've done better in China than we have in some other countries. I was disappointed, very frankly, with we didn't make as much progress in India. And tremendous, the whole Kodak India is headed by Indians, but I wanted Asia to have a much broader representation in leadership, and because the corporation needs that. And I think that, certainly whether you talk about global R&D, I mean, we have to think about, for American companies, global R&D may not be based in either Rochester, New York, or Schenectady for GE, or wherever in the US, but it may in fact be based in Bangalore or based in Guangzhou. So, any other questions?
Does Kodak, and with your dealings with the multinational companies in general, do they have, how much problems do they have with IP infringements? Last I'd read, I think 2004 from Barron's, was that over 50% of all the IP infringements have to do with Chinese companies and U.S. technology. Do you have a whole arm dealing with that, or how do you approach that problem?
The issue around intellectual property obviously is a major one. One of the reasons that we and I would highlight GE, because I know their plans well, invested so much in employee retention was it helped deal with this transfer of know-how. And the GE labs in Shanghai spent a tremendous time and focusing on their employees understanding their importance to GE. Because a lot of the materials development that they do there, they knew would walk out the door if they lost those employees. IP is a key issue. When I would deal with my contemporaries from other companies, the US government was always saying, give us a case, and we would have instances certainly of pirating Kodak product that looked like Kodak product but wasn't Kodak product, counterfeit in the market. We had some inkjet printer products that when we opened them up at a Shanghai trade show, it said firmware, Eastman Kodak Company, San Diego, California. I mean, it was a direct lift. But you look at the expense and you look at the yield of dealing with it, and it's frustrating. So it's got to be a big case. And GM has been the one probably beating the drum on the cherry. There's certainly been a lot of discussion by other companies. I think, and this is a personal opinion, that the laws will change as China develops more and more innovation and invention, and other entities outside of the country start trying to emulate those. And I think the laws and interpretation will be much more stringent. The government's concerned about it because they recognize that all companies, multinationals, will be nervous about opening up pure R&D centers if, in fact, the IPR laws aren't clear and more appropriately enforced. So it's in development. It's on journey at this point. Any other questions? There's one there.
My question has more to do with the kind of growth that both in growth direction in which both India and China are heading up right now. So as you probably know, China is moving in manufacturing more than a service-based industry, where India is making maybe a little faster progress.
Mm-hmm.
And so that makes these two growth models totally different from each other.
They are.
So I mean, that will also be a factor for a company to move to one of these two countries. And I mean, do you see any reason for such a diverse growth direction for these two countries?
Well, first of all, I think your comment is well put. The Indian government seems to have had a more targeted focus and investment, for instance, in IT, telecommunications, and certainly outsourcing. The Chinese government has been more open in terms of a broader opportunity, not just from a manufacturing, but a less targeted industry investment. And part of it is just the incredible growth of China and its hunger for consumer products, for commercial products, for durables, et cetera. The incentives from the governments are very differently. And so as a multinational, you make choices where it's going to be easier, where you're going to be supported, meaning financially and logistically more. And it has led Kodak to make different investments in India versus China. And I would have thrown, 10 years ago, I would have thrown Russia into the same conversation because I was the one that led photographic paper and chemical manufacturing in Russia. Because of its political environment and lack of choicefulness, I would be very reluctant today to put a major capital investment in Russia. Now that may change over time, but again, that's the context behind the business assessments that you make relative to investments in technology or plants, operations, markets, et cetera. But your comment about, one of the questions I had one time when I was speaking in India was, are you for C or for I? And meaning, are you for China or India? And my answer was, yes, I'm for both. Because I think there's tremendous opportunity, but different contexts that the governments are providing, and therefore companies will make different choices. Thank you.